Okay, let us continue. So last time we did a few problems, right, about Markov property. And the point, right, is that, while deciding if something has Markov property or not, the main thing, right, is whether you can decide the transition probability, right, or in another way, right, whether you can write down the transition matrix, which is, right, the same thing. And informally, if you can write down, right, the transition probabilities of the transition matrix, then it is a Markov chain, right? Simply because, of course, you can decide the probability of moving to the next step, right? Two stages in the next step, uh, based on the current step, right? And if you can't, and if you honestly can't, right, then it's not a Markov chain. But of course, right, that's just like sort of like a rule of thumb. The justification, right, for those things, or why you can or cannot, right, depends on the problem you deal with. And you, for kind of each problem, you want to point out precisely, right, like if you cannot and why that happens. And if you can, you have to write down the matrix correctly. And then we continue to talk about the Chapman-Komarov, right? I mean, not talk about, but like an application of, right, which is this one, right? And really, there's nothing to say much about this, right? It's really, the only thing is it's really a probabilistic statement, right? And you use the law of total probability to write down the expression you want, right? Use a Chapman-Kolmogorov to express the transition, right, probability. And the only thing, right, is to note that, well, I mean, this is an acceptable answer, right? Sorry. So here I missed, right? So moving from here to here, right? Moving from here to here, what I missed was a sum over I, right? And so that would be sum over ij, right? It's a double sum, right? Okay. And so the sum over I, right, is of course here. The sum over j, right, expresses here. So it becomes like, like a inner product, right, with a matrix in between. Okay. So let us continue to this one, right? So let's look at A first, which is, right, and I guess now we're gonna combine, right, those previous things we've done, namely that A, right, we're given a problem, we need to decide or model a Markov chain, right, for the problem, and then do calculations with that Markov chain. Okay. So our chain, right, clearly only has two states, right? Which is one, right, if the nth ball selected is red, and zero otherwise, right? So it's an indicator function. So is this a Markov chain? If so, given this transition matrix, yes or no? Can we decide? the entries of this transition matrix, namely P00, P01, etc. Any suggestion?
So when you're deciding the nth state of a Markov chain, you're supposed to look at the past history, correct? In order to decide the nth state if the process should be Markov. In this case, there's no dependency on history, right? So I would say it's not a Markov chain.
Yeah. So your argument runs along different lines that sound a bit not together. You said
Okay.
not dependent on history, but then not Markov chain, and then the state the end step should depend on the history. I'm not sure how those.
The most recent history, right? Like usually the nth step depends on the n minus one step or.
Correct. Right. So again, I mean, be careful of throwing in more words. I mean, I know you want to kind of elaborate and try to make things like kind of into your own words, which is good, which is a learning step. But on the other hand, be careful of putting in things that may not be as clear, right, as the property is supposed to be, especially with something like Markov, which is a little bit like, let's say,
Right, of course.
abstruse, right? So no, but so the point here again, right? This is why I keep going back to the same point, and this is it. Can we write down the transition matrix? If not, explain why not. If yes, give me the transition matrix. I think it's that, right? The more we throw in words, I mean, of course, when you say it's not, then we can trace down the sort of verbal reason, right? But if it is, numerical value is good enough. So I guess you're leaning toward no, right? But then now is when you kind of explain in words based on the context of the problem. Why not? Why can't you write down the transition matrix?
If you know what the last ball selected was, then you can write down the transition matrix for what ball it will be replaced with, but you don't know what the other ball is, so you can't write down the transition matrix for the next selected ball.
Perfect, right? Perfect. What you say there, I think, very, very detailed, and I think that's a great answer. Perfect. I'll just put my own way of saying it, and it's sort of along your line. But clearly, to know the probability of the next ball being red or not red, right? You must know the state of the urn before you select, right? Otherwise, how do you know the probability? That's it, right? It's clear. You must know what's the composition of the color in the urn to know the probability of selecting red. Agree? That's it's as simple as that. But the information we're given before is only right partially, or as your friend said, right? Exactly, a partial information, like just the one you selected. So you only know partial information about the urn. You don't know about the information about the composition of the color of the urn completely. So it's impossible, right, to write down the transition matrix for A. Is that okay? So either way, right, what he said is perfect. What I said is more on, what I need, but similar things. So no, right? Part A is no for that reason. Any question? Okay. So B, right? Denote the number of red balls immediately before. You see, now it's different, right? And so just to clarify, for example, right, what states can Yn take? What's the state space?
It's 0, 1, 2.
Right. You see already, even just superficially, right, we track more information. Again, I'm not saying that that's a yes or no signal, but usually, right, you see the theme here is you kind of need enough information, right, to decide. So more information seems we're on the right track, but let's see, right? So, okay, can we write down the transition matrix here? If we can someone read me the 0th row of this matrix?
I think it's 0.5,
What?
0.50.
0.5, 0.50. Do we agree? If there's no problem with this, can someone read me row number 1? If there's any question, do ask, right? But like I said, with transition matrix, I kind of wanted to let you guys work it out on your own, right? Otherwise, you will not get to the habit of doing this.
Can we just clarify if there's an equal probability of picking a red and a blue ball?
Sure, if there are 2 balls, right, then it's equally likely. That's sort of like the assumption of an urn with so many balls. Does that make sense?
Yeah.
Like there's probably selecting any single ball is whatever. But of course, if there are more colors, then you do that. But yeah, urn are always assumed to be equally likely.
Okay, thank you.
Sure.
We got 0.15, 0.6, 0.25.
Like this?
Yeah.
All right. So let me see, because number seems a bit interesting, right? Can you explain the 0.15, let's say? How does 1.15 happen?
So to get an extra red ball would be that a blue ball is selected and then a
Wait,
red
hold
ball
on.
replaces it.
Wait. 0.15 is
Oh, sorry.
one row to 0, right? Do you mean that, or?
Sorry. I was explaining the 0.25. Sorry. The 0.15 is the only way to lose a red ball is to take a red ball and then replace it with a blue ball. And so that's 0.5 times 0.3, I believe, which got me 0.15.
Okay, let's see here. Yeah, right. So I guess here also to clarify on reverse question, right? Yeah, selecting a ball is equally likely, but the probability of replacing the ball, right, is actually given by the problem. That's not equally likely, right? That's where those 2 numbers comes in. But yeah, selecting a ball, right, is equally likely, right?
I have a different set of numbers.
For which one?
The first row.
Yeah, now that I see that, right, I think the first row, because of the replacement, right, may not be 0.5, 0.5. Okay, so go ahead. What would that be?
First row meaning like
0 row. I know what you mean.
No,
right?
no, no,
Yeah.
no.
Oh, it's the 0.5, 0.5?
I mean, I still agree with that. I just don't agree with the
Oh, okay.
that part.
Okay, go ahead.
Okay, so right now there's 1 red ball in the urn. So if you replace it with another red ball, you map back to state 1. So the middle value should be 0.7. And if you select a red ball and then you replace it with a blue ball, then the state space goes to 0. So that should be 0.3, the first entry. And then the last entry should be 0.5. I don't know.
Wait, hold on. So tell me your numbers.
Oh, 0.3, 0.7, and I'm not entirely sure about the last one.
Yeah, already there's trouble there, right? Because
Okay.
0.3 and 0.7 already filled in the whole row. And clearly, I think you can go from 1 to 2 here, right? Definitely, that's a non-zero probability.
Okay.
Correct? So yeah, right. Clearly, your answers have a hiccup somewhere. So okay, let us go through your point 3 for just to see the logic. Right? How do you explain the point 3? 1 go to
Actually,
0.
never mind. Could you explain again how you got
4 and 5.
yeah.
So the gentleman who just explained, do you mind repeating your argument?
Yeah. So in order to lose a red ball, you have to pick the red ball from the urn, which is a 0.5 chance. And then you have to replace it with a blue ball, which is a 0.3 chance. And so you just multiply that and you get 0.15.
You
And
multiplied the
that's the
probability
only
by
way.
0.5 because the probability of picking the red ball is 0.5. That makes sense. Thank you.
Yeah, that's what Riva asked, right? Picking the balls, are they equally likely, right? So picking the ball and I guess replacement are independent actions, right?
I
Yeah.
understand. Okay.
Cool. So we're good. Okay, last row, please. I think last row is 0.5, 0.5 this way, maybe by symmetry. Pure guess.
I think it should be 0 and then 0.3, 0.7, right?
Yeah, that's what I got.
Oh, okay, sorry. I was not thinking. Good, good. Glad to have students who watch out for the problem. All right, do we agree? All right, so in this way, it's a Markov chain, right? Very good. So let's start with C, right? So C here, find the probability the second ball selected is red. And we need to pay attention to the initial composition, right? So this, with respect to P, right, which is part B, all right, we'll use the matrix P here. How would you express C? So notice, right, this is a conditional one. I mean, it's not a conditional one. You need to do law of total probability to resolve this, right? You need to know the state of the urn where? On the first step, correct? To know. Agree? So C initially would be something like this. It's going to be 1/2 times probability y1 equals to 1 plus 1 times probability y1 equals to 2. Do you understand?
Can you explain that further?
Yeah. So y, right, from the notation of part B is the number of red balls at any step, correct? In the urn. Now we want to ask if the second ball selected, right, is red. Agree? Meaning that that's a second step, right? And the second step. So notice that this part C kind of refers back to this one right here, which is not a Markov chain, right? But by the composition of the balls in the urn, we can figure it out. Namely that, right? Probably x2, which is the red x2 equals to 1, right? Something like this, if you want to be fancy about it. Right. So basically, based on this number of red balls in the urn, you can know if the second pick is going to be red or not. But I take away, right, the case that there's no red ball in the urn because clearly there's, no. Oh, so Yeah, right. That will be 0. Do you understand?
It's 0 for the case I equals 0 because the initial composition is necessarily 1 red, 1 blue, right?
No.
Why?
So time-wise, right? I think initial is here, which is step 0, I think. Right, and then step 1, which is whatever. And then I think step 2 here is where they ask if you select the red. That's how I understand it, right?
Oh, okay.
And of course, again, right, the confusion here, which is fine, but that's the whole point of this problem, is there are 2 processes going on. There's a process of selecting the ball and look at its color. But that process which you're interested in is not Markov in itself, as we concluded in part A. So we need to turn into the composition of the urn, which is part B, to track the composition. But you still are interested mainly not on the composition, but on the color you selected. So then you have to condition it, right, on the state of the urn before, right? So this is like you select the red and then you would change the composition of the urn, right? This is a step in between. Does that make sense? So this here would depend on the composition of the urn before you select, which is state 1, which is Y1. Does that make sense?
Yeah, thank you.
Mm-hmm.
I'm just a little bit confused about why we're ignoring y1 equals 0. Because if there's no red balls, why can't we still pick a red ball?
No, that's the whole point. That's why Y1 equal to 0 multiply with. If Y1 equal to 0, we will multiply with 0. That's what we don't include it. The 1/2, 1, and 0 are the probability you will select a red ball based on the composition of the urn, right? Does that make sense? 1/2 is if the urn has 1 red, 1 blue, you pick it with probably 1/2. 1 is if the urn has 2 balls, 2 red, you pick it with probably 1. And of course, right, if it has 2 blues, you pick the red ball with probably 0. These are the conditional probability of picking based on the state. That's that one. Are you okay?
How did you get the coefficients 1/2 and 1?
Say again?
How did you get the coefficients 1/2 and 1?
So again, right? 1 means
The
red.
correct state of the urn is 1 ball. Or 1 red
Yeah.
ball.
1 red, 1 blue. So the probability you will pick a red next is 1/2.
Oh, okay.
Again, right? I think
Can
you
you
guys
read
are
it
just
off our matrix somehow?
read what off. No. So see, that's the point. The matrix is for tracking the Y. But once we figure out the Y, then from there we will know the probability of picking the red on the next state.
Okay.
Right? The picking of the red itself from part A is not Markov. So we need to rely on the status of the Y chain to figure out the probability of selecting the red part. Just that, right? And we just have to kind of separate out the notation clearly, what we mean by which. Okay, so here's the thing, right? Something like this, if you want. So basically, right, initial, right, state 0, right, 1 red, 1 blue, okay? Then there's kind of like this kind of X1, which is behind the scene, where, it tracks whether the first ball select is red or blue, right, whatever, which will inform Y1, correct? Then you will have X2, which is the pick red, pick blue second ball, which will inform Y2. Do we understand now? But clearly, right, the X process depends on the Y. And X itself, if you just look at X itself, it's not a Markov chain. So you need to condition X2 on Y1.
X2 is the which ball is picked on the second pick, right?
Correct. And which is, I think that's what they mean here, right?
But then wasn't Y like 2? Wouldn't that be the composition of the urn right before the second pick?
No, that would be Y1. Think I mean, that depends on what notation is. I think we call this Y0, isn't it?
Sorry, could you just scroll down? I kind of forgot.
Yeah, go for it. So this is just really numbering, right? What we mean by which. But I would argue, right, the initial composition is 0th time, haven't done anything. Then first ball you pick would inform Y1. Correct?
The initial, sorry,
Right.
but the initial state of the urn is right before the first pick, right?
Yeah. So that's why.
So
Yeah.
wouldn't that be Y1?
I agree with him. That's the notation in the previous part, right? YN denotes, where is that? In part B, it says let YN denote the number of red balls in the urn immediately before the nth ball is selected, where N must be equal to 1.
Sorry. Okay, fine. Okay, I see. So I see. Okay, so I neglected that part of the notational problem. That's fine. So if you want, then right, then we call this Y1. Then X, then yeah. So X1. Okay, then this will inform Y2. Okay, fine, like that. So that's what that would mean. That would correspond more to what you guys think, right? Then I would need to change all this to 2. Yeah, okay, sorry. I did not pay attention to that notation of the problem. My counting is starting with 0. Right here. All right. Would that make more sense now?
Yeah.
All right. But anyway, right, the point is whatever notation we use, it was just a one-step transition from the initial distribution, right? So that would be 1/2 times what? Y2 equals to 1, right? Initially, what's there we're at? We're at 1, right? So 1/2 times P11 plus 1 times P12. So that's the answer to part C. Do we agree?
So the transition probability, Pij, is equal to the probability. It's not a marginal probability, right? It's a conditional. You're not. It's a transition probability.
Yeah, it's conditional, of course. But again, the initial distribution is 1 red, 1 blue. So we know initially we are state 1.
Okay.
Right? Good. Any question?
Yeah, I'm still just a little confused again with what Kathy said about the coefficients with the
Go
0,
ahead.
1/2, and 1. Do you mind explaining it one more time?
Sure. So this is the state of the urn, right? Right before we pick the second ball, right?
Yeah.
And so if the state of the urn has no red, then the probability we'll pick the red on the next will be 0. If the urn has 2 reds, then the probability will pick a red right after that is 1. If the urn has 1 red, then probably we'll pick a red after that's 1/2. That's all we're expressing.
Oh, okay. Thank you so much.
Okay. All right, so now let's answer part D, right? Hopefully part D will be quick now. What should the answer to part D be?
Similar
the answer should
setup,
be.
right? With
Yeah.
the summation. So sum
So
from
what?
I equals 0, 1, 2.
Yeah, well, we can read out the answer right away, right? Can't we?
Okay.
1/2 p cubed on 1 plus 1 times p cubed on 2. That's it. Right? The logic is simple. You transition 3 steps to step 4. You're at state 1 initially, so you can only move from state 1 to state 1 or state 1 to state 2 to be able to pick a red ball. And those are the probabilities correspondingly. Are we okay? I mean, the sum is just to explain to you, right, how the probability is calculated. But once we get the pattern, we just write down the answer. Any question here?
Why is it p cubed and not p to the power of 4? So
Again, right, that's why you corrected me. I mean, not corrected, but right, we count initial state as state 1, right? Initial step is step 1. So the fourth ball is the ball you pick after you move to step 4, right? From step 1 to step 4 takes 3 steps. Or if you want, the answer to C, right, for second ball is P. Then just logically, the answer to the fourth ball must be P cubed. Agree? Any question? Okay, so let us move on to the next one. All right, so here this is where we would talk about on the last part of the lecture. Okay, so we've talked about Markov chain modeling, right? As in how you encode the state, right, to have enough information to decide the probability, right? You move on to the next step, right? That would be these two. But there's one more thing, right, which we did not discuss, which is efficiency, right, of encoding. Just because you want to encode information doesn't mean you want to encode everything, because that would be a lot, right? So now that's a theme, but another theme is, here. I'll just tell you, right? So remember, right? Let's say the problem of tossing a coin, right? Whose probability of getting head is P, right? And we find expectation, right? Remember. So let's say, right, probability of, right, so X, let's say, right, X1, X2, etc., right, IID, Bernoulli P, right? So probability Xi equals to 1, right, is P, right? And we want to, right, N3, right, is the first time we observe 1, 1, 1, right? Or if you want to look at the coin, right, head, right? And we have found, right, expectation of N3, right, by conditioning technique, right, which is 1 over P, 1 over P square, 1 over P cube, remember? Right, by conditioning on N2, right? So, but notice, right, this is just very partial information about N3, right? N3 is a random variable, correct? N3 is a stopping time. It's a time, right, that we observe 3 consecutive heads, right? The first time we observe 3 consecutive heads. So if you look at N3 as a random variable, then first of all, right, notice that N3 can take on what kind of values? 3, 4, 5, 6, etc., right? And so as a discrete random variable, the first thing you want to know is the mass function of N3. Right? But of course, you see the point of like more advanced probability is some questions may be easier to answer than the other. We found the expectation of N3 before we even found the mass function, right? But let's go back and let's just run a few things to see, to demonstrate to you, right? What's probably N3 equals to 3? Let's see if we can even get a hang on what we're discussing here, right? What's probably N3 equals to 3?
P cubed, right? Well,
Correct, right? Of course. What about N3 equals to 4?
P cubed times 1 minus P.
Uh-huh. Go ahead.
Is there any
No question.
notation also? Does it,
Anyone?
like,
It-
never mind.
Yeah, there's some other Markov chain behind the scene, but right now, if you just focus on this sequence, then it's IID, okay? It's independent. That if that's a sequence,
Never
there'll
mind.
be yeah. Okay, let's try one more time. N3 equals to 5.
1 minus P squared and then P cubed times P cubed.
Are you sure?
Yes.
I would argue that that would not be right because the first flip could be a head.
Exactly. Now things start to be a little bit more, right? It's just the first time to get 3 heads. It didn't say everything before, it must be tails.
I
Right?
see.
So when you say 1 minus P squared, you just say 2 tails, and then exactly Reapers pointed out, right? The first one can be a head, right? Correct? So the first one doesn't matter really, right? So I think it's 1 minus P times P cubed again. I believe, right? Because the first one doesn't matter. Head or tail is fine. Second one must be a tail. The last 3 must be heads, right? Correct?
Yeah, that makes sense.
Okay. So, but you see the arguments start to be a bit more sophisticated. Anyone wants to give me the answer for this? Right?
I have a question about this one, which is that would this one be much more complicated because it also is predicated on the fact that, like, you can't say the first 7 don't matter because what if from 3 to 5 they're all heads?
Perfect. You just point out exactly the point. Perfect. Right? That basically, right, the argument on point 5, where we say that the first doesn't matter, is sort of like just peculiar on the fact that, right, we have 5 coins and clearly the first doesn't matter. But when you go to like 10, for example, then you cannot say, right, you cannot bootstrap on the same argument and say the first 7 or first 6 doesn't matter. Because, right, the whole point is that the 3 heads cannot twist, the 3 consecutive heads cannot happen before, right, step 10, correct? So clearly, for example, right, we know something like head, head, head. So this must be a tail, right? That we know, right? Otherwise, you know, you will have 3 heads sooner than that, right? But before that, all you can say is no 3 head-to-head before that, right? But more precise answer, right? It's not easy, correct? Okay. And so the point I'm trying to say here, right, is that for this random variable, right, the whole point of, or what we did before was kind of trying to find expectation, or, we can stretch ourselves and try to find a variance, right? But those rely on, techniques of conditioning, right? Double expectation and total variance, that kind of thing, which is easier. But when we look at like a more detailed picture, like the mass function, then it starts to become, right, much harder, right, much more complex, because the patterns or what we have to analyze becomes more, right? Okay. So now, this is exactly the reason why we will look at the next technique, right? Which is to use Markov chain to answer this question. Basically, we use Markov chain to track a pattern. All right. That's the theme. All right. That will be the theme from now until next lecture or so. And you can consider this as an application of a Markov chain, if you will, right? So let's take a look. So, right, obviously, if we want to, right, track, let's say, the probability, right, that the 10th step, right, or the head-to-head happens at the 10 toss, right, then we could, as a natural thing, track, right, all possibilities, right, of 3 consecutive tosses, and let xi denote, like, let's say, a chain, right, that keeps track of all those information. Okay, so far? So basically, right, this is a very, let's say, natural thing to do. No deep thinking involved yet, right? We're just tracking the last 3 tosses, right? What the outcomes are. Okay, so far? So several questions come out of this, right? So this, right, is basically an encoding phase, right, to begin with. But notice, right, just because we encode something doesn't mean it's successful. So the first thing we need to know is what? Transition matrix. Can we write down a transition matrix, right? Because if we can, then it's a Markov chain, and we can use Markov chain, right, technique, namely, right, the only technique we have now is Chapman-Kolmogorov, but right, we can use Chapman-Kolmogorov to calculate the probability. But right, so that's the first thing. The second thing will be then, right, to adapt the probability we can calculate with xi, right, namely Chapman-Kolmogorov will allow us to calculate things of this type, right? Probability, let's say xn equals to I, right? For any n, any I, right? I mean, I here from 0 to 7, right? N is any time, right? Okay, but we need to now adapt that to the question of, let's say, probability of n3 equals to 10. How do these two match? Do you understand? So that's the program. That's the theme of the investigation. And knowing this motivation is exactly why, like, there are a lot of machineries and techniques that will go from here all the way to next lecture. So it's important, the motivation and why we want to do what we do, and the translation and things like that. The whole point is none of this is obvious. If you do it wrong, you won't get the right answer. So any questions so far about what we're trying to do here? All right. So let's So let's start with the first step, right? Transition matrix. See if we can do it. Sorry, trying to see how. Okay, like that, right? So first of all, right, notice our matrix will have 8 states, right? 0, 1, up to 8, 7. Right, and again, right, we're tracking the result of the last 3 consecutive tosses, right? So if you follow what we're doing, right, tell me, let's say the first row, right? What would the first row be here? And by the way, right, so the result is left to right, meaning, right, this is the last one next to last, 2 steps before last, that kind of thing. Is that okay? So go ahead.
Yeah, for the first row, I have 1 minus p for 0, 0, and then for 0, 1, I just have p, and then the rest are zeros.
Right, correct, right? Because telltale clearly can only go to telltale or telltale head. Is that okay? And let's do the next row, and then I think we'll kind of get a pattern, right? What about the next row?
It would be a 1 minus p at 1, 2, and then a p at 1, 4.
Yeah. So let's see, right? 1 here, telltale head can clearly only go to tail head head, which is a 4, right? Will probably p, or go to tail head tail, which is a 2, right? Correct. Okay. So doing this, we can kind of write down the matrix. Right? Any question? Good. So all right, we still have a few more minutes. So that's P, right? And clearly then this chain as I track, right, is a transition matrix, okay? But let's kind of note something already kind of awkward about this transition matrix. The first thing, right, is that notice if I note xi, right, what do I mean by xi? As the outcome of the last 3 tosses, right? So timing wise, right, if we kind of think of I as the time of the coin toss, then where should I start here?
3.
Right, right. So naturally, whatever that means, right? In terms of the way I encode the chain, somehow I must start the chain at 3, right? Okay. So that's a bit weird. But let's say, right? So because I use my clock as the coin toss, right? The clock of the coin toss, right? So in that sense, let's say if I want to find probability x10, let's say equals to 6, let's say, right? Or let's say 7, right? How would I write that? How would I write probably x10 equals to 7? Is it?
I mean, that would
Go ahead.
that would be p that n3 equals 10.
P. Sorry, say again.
So p
P
at
to the 10 power.
no, I said that. I thought you were asking for something else. Never mind.
Yeah, no, right. So that again is kind of tricky. I'm saying at the 10th toss, right? I observed the pattern head in the previous three, right? That's x10 equal to 7. Agree? But now in terms of my matrix encoding, what would that be? So here, note another awkward thing. First of all, right, because my time start at 3, right? I can only do P. Okay, so this 7 may clash with something else, right? So let me just say 4, okay, just to demonstrate. But basically, I have to do P to the 7 because 10 minus 3. I can only take 7 steps. Do you understand? So I can only take 7 steps with my transition matrix, right? Because I define, or somehow it seems that my chain naturally start at the clock at 3, correct? But P to the 7, right, is not enough, right? Because I want to do P to 7, end up at 4, right? But where do I start? I can start at any state, right? I going from 0 to 7. So I have to multiply that with pi I. Where what is pi I? Do you understand? Pi I is the initial distribution after 3 tosses. Does it make sense? Any question here about the setup? Right. So because we track 3 tosses, right? 3 consecutive tosses. That's why sort of we have to start at step 3. And so to move to step 10, right, it takes only 7 transitions. That's why 7, P to 7. But then, right, because we start at step 3, we don't have like a definite initial state, right? Initially, we at step 3 can be at any of these things, right? So we need to multiply with the initial probabilities of getting there. And then transition from there to the desired state, right? Of course, the desired state here is 7, but I was afraid that this 7 might be confused with that 7, right? But now that you understand that, we can replace that with a 7 if you want. Do you understand? Any question? All right. Yeah, go ahead.
What does P to the power of 7 represent? Going
The transition, right? The transition
7
probabilities in 7 steps from a state I to a state J.
Correct. Okay.
Right? So that's because X here, right, tracks the outcomes of the last 3 coin toss. So basically, right, it says here, this statement in English is at step 10, right? At step 10, you observe head, tail. This is 9, 10, 8. Like that. That's what it's telling you. In the sequence of coin toss. This is what it's telling you. This calculation right here.
That makes sense. Thank you.
All right. We're good? All right. So now let's give you the quiz, right? And we'll continue right after the break. So for the quiz, right, let's just do this one. Hold on, let me see. Is that okay? Find expectation next. Okay. Any question before we take a break? All right. So we'll continue at 11:35. Okay, let's continue. Any question before we continue? All right. So again, right, these are important in the sense that if this is the first time you see these things, right, may seem a bit difficult, right, to follow all that we're doing. So you ask questions, okay? But to recap, right, basically, we want to have a Markov chain, right, that tracks some pattern. And the pattern we're tracking here is head, 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 right? Or, whatever, right? Could be some other things. We just pick head, head. And so we design, right, basically just naively, maybe, a Markov chain, right, that track the state of the last 3 coin tosses, okay? And, right, it has 8 states, right? And we write down the transition matrix. Right, we write down the transition matrix, right? And then we conclude, for example, right, let's say, I will move to 12, okay, just to avoid the coincidence of the time and the state. Let's say probably x12 equals to 7, right? Will be the sum I equals to 0 to 7, right? Of pi I, p, right? I, p to the 9th, I7. Right, where pi 0 is 1 minus p cubed, pi 1 is 1 minus p squared times p, that kind of thing. Are we okay? And again, right, so x12 equal to 7 would tell us that the coin tosses, right, 12, 11, 10 are like that, okay? So now let's go back to the question we want. The question we want, right, is actually the probability of n, right, and the first time to observe the pattern. And notice, right, now that we're getting close to what we want, meaning that, right, notice with all these states, we can not just track head, 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 we can track head, head, tail, head, right, all those things, okay? Which is much richer than, right, what we did before, where we can rely on some special ones. But let's just, for now, address an important question. Is this equal to probability n3 as we define it equals to, or you know what, for now, let us just do probability, right, n head, right, just to know what pattern we're tracking, equals to 12. Is this the probability we want?
Yes.
Yes, so we're done, right? Hallelujah, go home. Enjoy our break. Is that true?
You have x12 equals 7 doesn't really say that there wasn't any triple heads before that.
Correct, exactly what Riva said, and now what you just kind of reiterated, right? x12 equal to 7 just says that yes, right, on the 12th step we did get the triple heads, but that's not what we want, because we want the triple heads only then and not before, right? So nope, not that.
Then it's the product, right? Like of n3, well, n HHH equaling 12 and then not equaling 11 all the way up to 3.
Okay, but notice, right, there's a device here that I think you and maybe other students too are not quite getting used to yet. That is, just like the earn question, the red, blue, Markov chain, right? In a lot of these problems, Markov chain is a device that you will use to indirectly or whatever get to what you want, right? So for example, tracking the states you earn is a Markov chain that will allow you to know, right, the probability of the red you pick. The same thing here, right? Yes, we want N3. but the device we want, or what we want to have to work with, is the X Markov chain, right? So yes, what I'm saying is you're referencing to the N, right? N3, but you need to reference the X because that's the only thing we have device to work with via the transition matrix. Does that make sense? So what would that be in terms of the Markov chain X that we just model? Not that you said what you said is wrong, right? But what does that mean correspondingly in terms of the Markov chain that we just modeled in terms of X? So let me, let's and in terms of X, what would that be? Clearly, right? X12 must be 7. Because
Probability of X12 equaling 7, and then X11 all the way to 3 not equaling 7.
Exactly.
And then you can just write that with big pi notation to simplify. And then you take the complement instead of summing.
Hold your horses. You're
Okay.
good, but there's still a lot of things to do here. Good. But we'll do it one step at a time. Great. Right. So all right. So what your friend just pointed out is very good, right? This exactly would correspond to this. Are we okay so far? So we want, right, the chain to avoid state 7, right? All the way until step 12. Yes, that would be exactly N12, N3, and head equals to 12. Correct? And this, right, this structure, just to point out, exactly gives rise to what we study next lecture called the path probability of a Markov chain. Okay? In other words, because of things like this, we're more sophisticated now. We don't want just a step, right? Like, so let's say X12 equals to 7. We want to dictate the whole path. And we want statements like, I want a path, right? Eventually we'll do something like this. Let's say the start at 3, ends up at 5 on step 12. In between does not go to 4 and 6. Okay. That would be, let's say, something that we'll study in next lecture. Now, of course, right, we will have to think of a problem to demonstrate, like in English, why this will be interesting. But you can see, for example, it's going to be a subcase of that, or is a more general case of that, right? Where we want a path that avoids state 7, but end up at 7 and step 12. Okay. All right. Now, having said that, if you understand everything and you have no question, if you have question, ask. Okay. If not, how do we calculate this probability? Sorry, I can't pronounce it. Kayita? Okay, sorry. How do you pronounce
that's
it?
okay. It's Kyati. It's
Kyati. Okay.
You can call me Kathy too. That's fine.
Okay. With a KH or just Katie? Kati, right?
Well, you can call me like Kathy, like Kathy, I guess.
Okay,
That's okay.
Kathy. Okay. All right. Cool. So yep, Kathy. So what do you want here? What do you propose?
Well, this is a joint probability, right?
Yeah.
And there's a dependent structure, so we have to use the transition probability matrix.
All right. Yeah. Good. Right. Great. So what you said is very good and very on point, that there is a dependent structure here. And that's the whole point, right? That's the rub. And that's the whole point of stochastic process, right? As I emphasized, right, on Monday, that the difference between this and an IID sequence is that calculation like this requires much more care and technique, right? For example, if these guys were independent, right, then the calculation will be done in one swoop, right? You just multiply the probabilities, right? End of period, end of question, correct? But exactly because of the dependent structure, right? Path probabilities or questions that are interesting in nature, right, becomes much more nuanced and requires, right, more thought, more techniques. But now, right, to dig deeper, as Kathy proposed, transition probabilities. Okay, care to elaborate? How do we use transition probabilities here?
Well, first we have the initial probability distribution.
Okay, that's pi I, whatever, right? Okay.
Equals 3, right?
No,
not
pi, notice the I here refers to the states. So we start at step 3, right? Step 3, we start at state I, right?
right.
Okay, and then we need to step to step 12.
I'm not
Or-
sure.
Yeah, so transition probability actually is not helpful here in this way, right? Suppose I say, right, let's say I want step 4, step 5, right, step 6, let's say I want state 2, state 3, state 0, whatever, right? You know, so I specify the path, right? Then it will be something like this: pi I, p I2, p23, p30, p04, etc. You understand?
Yeah, but there are
Because
multiple
you
possible paths here.
exactly, and because the only thing you say is that you want to avoid state 7, right? So what you're saying is that this can be 0 to 6, 0 to 6, 0 to 6, right?
Yeah.
Now you can still do that though. You can still do a sum, pi I, p I, j, j not equal to, 7, and p, j, k, k not equal to 7, that kind of thing, right? But first of all, that's a very painful thing to write and to code, because that's a lot of sum within a sum within a sum. Does it make sense? Because the whole point is the nature of not 7, right? Point to a lot of possibilities. All right. So this gives rise to, or this motivates the next technique that's very important, called the absorbing state. Absorbing state will allow us to calculate this much more elegantly. Okay, but first you have to understand why this is painful. Like with transition matrix, you can express it using transition matrix, but I don't think anyone wants to. Okay, any question about this? Okay, so then, right, the next point is about absorbing state, which exactly goes hand in hand with these kind of path probabilities. Okay, so pay attention to this. Absorbing state or absorbing class will be exactly the technique to, or you need to master this to be able to write down the path probabilities, okay, that we desire for now in the next lecture. So the idea, right, is that, okay, state 7, let's say, is the important one here. So let's go back to the transition matrix, right? Everything else being the same. But what happens if I make 7 into an absorbing state? So clearly now I don't want to call it P, right? I'll call it Q. So Q, right, is going to be a modified matrix from P, right? So basically, the idea is that given any Markov chain with a transition matrix, I can always modify it by turning some states into absorbing states, right? Why? Because that new chain, okay, adapted from the old chain, will allow me to do certain calculations much more easily. Okay, so basically this Q matrix, right, will be associated with a new chain, right? Let's say Y, correct? Where now state 7, right, Y will behave very similar to X with state 0 to 6. But state 7 of Y is absorbing, meaning once you enter state 7 of Y, then you're there. Okay? Then let's kind of ask you this question to see if you understand. So note this expression, right? What if I, instead of using P, I use Q? Then what have I got there? In terms of logical statement, what have I computed?
The probability that by step 12 you will have hit a head-head-head.
Excellent. And so in terms of X, that would be probability xn equals to 7, n equals to from 4 to 12. Do you agree? 4 because, right, I kind of include 3 here, right? So so here, I guess, you know what? Here, this is still awkward because I sum over I. Let me do pi 3. Sorry, pi 7. No, it's not pi 7. How do I do this? Let me think. You start at step 3. You multiply. Okay, sorry. So this is still awkward. This will be sum I from 0 to 6 pi I. Okay. Yeah, sorry, because 7, right? 7 is where I was absorbed, right? I was at state 7 at the beginning. So I need to take that out. Okay, so we'll explain that, because once you make something absorbing, it's kind of awkward to relate back to the original state. So we have to kind of do that. But here, right, this is probability that you are at state 7 from step 4 to step 12. Do we agree? Do you understand?
I just have a question about the 6. Why was that modified?
Yep, because this is corresponding to pi I, which represent the probability you are at that state at the beginning. You understand? But notice we do Q here, right? So pi 7 represent the probability that you are at state 7 at the beginning, right? But in terms of the Q matrix, if you are at state 7 at the beginning, you cannot move anywhere. Does that make sense? So it's kind of like so what I'm saying, right? What I expressed by this is the probability that you are at the other states at the beginning and then move to state 7. That's why n equals to 4.
I see the point.
Right? And then if I want, right? Right? And sorry, so here, right? This also should say that x3 not equal to 7. Right? So now if I want, right, probability x3, sorry, n equals to 7, n equals to 3, etc. to 12, right? I would do sum, right? I from 0 to 6, pi I, p to the 9, I7, plus pi 3. Now, plus pi 7, sorry. I could include the 7 in here and the calculation might go through, but I would rather, right, isolate it out just to, I think I could include a 7 in there. I don't know. For now, my brain works like this. I think, right, if you give me some time, I think I can include 7 in here and then just get that. But just to be careful, right, because 7 is absorbing with the Q matrix. So I want to separate out, right, the action of non-absorbing and then move to absorbing, right? And then add the probability of getting absorbed at the beginning separately. Are we okay with this? Is there any question?
So it's q to the power of 9 because you're going.
Q.
Oh, yeah,
And-
that's fine.
It's Q to 8, right? No, Q to the 9. That's correct. Q to 9.
Why is it q to the 9? Just really quick.
Because still, right, we are starting at step 3 and move to step 12.
Right.
Still,
Okay.
right? But the whole thing is I'm isolating state 0 to state 6, which are non-absorbing as one of my analysis. And then I throw in the 7 as a separate one, just to not mess around with that, right? Because you see what I'm trying to say, from the Q point of view, once you're at 7, you stay there, right? So I don't want to start at an absorbing state and then throw that in. I think you can still do that. That might still work, but right now I'm kind of.
Yeah, that's fine.
Yeah. So I think, right, I'm 90% sure, let me just put it this way, that this is equal to sum I equals 0 to 7 pi I q to 9 I7. I think with the Q structure, it should work. It's a bit awkward like this. I think 90% sure because I didn't check it, but I think it works because basically pi 7, right, if you multiply with this, it'll just stick pi 7 out. So anyway, right, that's a minor technical point. But what I'm trying to say, right, is that, right, by turning a state into absorbing, what you get, right, is the probability that you are in the absorbing state, right, at or before step 12. Correct? So now, long story to go back to where we are. So how do we express probably N3, right, or N head equals to 12 now in terms of the Q matrix? Yeah, I think let me increase this to 99. I'm 99% sure now. Okay, yeah. So how do we express this probability of N head equals to 12 using the Q matrix?
So the previous expression you just have up says like xn being equal to 7 all the way to 12. First of all, that
no, this is or, right?
Or that makes more sense.
Of course. So again, right, the logic of the absorbing state is like this. You start somewhere, right? This is step 3, step 4, step 5, etc., right, up to step 12. You can move to state 0 to 6, whatever, right? Or 0 to 6 and 7 too, right? But 7 is special in the sense that if at any step you ever step to 7, then you will stay there forever. right? Because 7 is absorbing, right? So that's why when you multiply Q, right, using the Q matrix, right to a 9, I7, you're saying you transition from state I to state 7 in 9 steps, right? But of course, you could have been at 7 before that and then get stuck there. That also counts moving from there to the 9 steps. Does that make sense? So that's why it's an or.
Yes.
You could
Okay.
have been absorbed anytime before that, and then you'll still stay there.
Can we understand the xn being equal to 7 at either time step 3 all the way up to time step 12 at any one point?
Yeah. So
n
you got
3 being less than or equal to 12, like, is that what that statement reads in terms of n?
like that? You mean like that?
No. Exactly what you had before, and just say that probability is equal to the probability that n3 is less than or equal to 12.
Correct. Exactly. This exactly is probably n2 equal less than equal to 12. Exactly.
Less than, but we want equal to. So
Yeah. So now it's easy, right?
yeah, we would do n3 less than or equal to 12 minus n3 less than or equal to 11.
Exactly. And that at least conclude the story for now in terms of what we want. All right. So to recap the story, right? There are a lot of techniques and information going on here. Sorry. The first, right, is to encode, right, the pattern you want to track. Then write down the transition matrix, right? And, there's some initial distribution that is the legacy of this way of encoding. We'll talk about that later. And, right, so here, I guess we want to 8, right? We will have to make that state absorbing, right? Because otherwise this will include, right, the probability that the pattern occurs before that, right? So in terms of Markov chain, it's very simple. You want 12, roughly speaking, or you want 7, right? In this sense, it's 8, right? You want 8 to be the first time the chain enters state 7. That's it, right? In terms of the Markov chain, right? That's what you want, right? You don't want the chain to be at state 7 at time 8, but you want it to be the first time, right, that the chain enters state 7, meaning that you want the chain to be not in state 7 before that, okay? And so that's why you want to make whatever you want absorbing. So, right, basically you want to avoid, right, state 7 before a certain time. I'm not saying that making it absorbing will do that, but this is a technique to address that kind of question. All right. And so, right, that's just a modified matrix. Yeah, so the young me back then, right, was just pretty confident that this is the case. So no need to separate the two, right? And then like that. Okay, any question about all these steps? All right, so right, we'll see this pattern or this theme recur, right, again and again and again. So make sure, right, you understand all these steps.
Really quick.
Yep.
So we can only do this because none of the other states are absorbing, correct? Like 0 to 6.
Yeah, or frankly speaking, we're just tracking head, right? But here's another one that would be interesting for you to think about. What if I want to have the first time to reach head, and or head, tail, head? Why not, right? I could be interested in such a time. Does that make sense?
Okay, in which case you would make the HTH, I don't know which number that is, state also absorbing?
You would make both of them into what we call absorbing class.
Absorbing.
Yeah, we'll make both of them into an absorbing class.
Okay.
So we'll address that next. Yeah, and that, right, but it's exactly the question I was looking at here. You can travel, but you will avoid a certain number of states throughout your path, right? So yeah, that's again why we want to study technique of Markov chain, because once we have the general machinery, maybe clunky as it is, you can modify it and it can be more adaptable to many purposes, right? Okay, any other question?
Last one. So if you look at our matrix P, it has a very interesting structure. Is there any type, like, can we call it a certain type of matrix?
Not sure.
Because there's only, for every row, there's only 2 entries that.
Yeah, the reason, right? The reason, again,
makes sense. Like,
there could be something here, but I would say it's sort of cheesy and not worth our time. The reason is obviously because of our encoding, right? That's all there is, right?
Right, of
Because our encoding, and at any point, clearly we can only flip, right, a coin to a next 2 possibilities. So it's not that interesting from that point of view, meaning that clearly it must have 2 possibilities because the coin has 2, right? So I don't think there's much going on here.
okay, yeah.
Yeah, but I could see a deeper theme somewhere, but we have to kind of pose that theme precisely. Yeah.
Thank you.
Yep. Any other question? Okay, but now, right, just let's continue with this theme. So, right, I hope you are convinced, right, that this way of encoding will be able to address all possible questions you can ask about first time to a certain pattern, right, for a coin toss, let's say. Yes? Now, but let's see. Let's say that I'm very excited, right, about this technique. I just saw it. I'm super eager. And I want to find the first time to track head, because why not? It's called N5, right? I want to find probably N5 equals to, let's say, 40. Yeah, why not? What would that entail? This would entail designing a matrix that design the Markov chain that track the last 5 consecutive tosses, right? And how large is such a transition matrix? How many states are there?
32.
32, right? Well, I notice we just increased 2 more coins and we already blow up, right, the matrix to a state where I don't think I want to write on the paper, right? No way, right? And so what happens there, right, is in CS lingo called an exponential growth. I mean, math too, but I guess I'm referring to more like complexity. And sort of, right, whenever you saw an exponential increase in complexity, if you have to, that's the only way, okay, right? Whatever. But you want to step back and see if you can do it more efficiently, especially as Kathy pointed out, right? And actually, it's not that this is interesting. Actually, it should be the opposite. It's not interesting in this sense that, well, apparently at each state, each row, you only track 2 entries. It has a lot of zeros, right? A lot of zeros is a lot of waste, a lot of, it's called sparse matrix, right? But anyway, even if it's with a sparse matrix structure, if you have like exponential growth, right? What if I want to track a pattern of 10, right? 2 to the 10, right? That's a lot. So that goes now to this thing. Minimal and sufficient. Okay. The reason is as followed. Okay, right? I want to find the first time to 3 consecutive heads, right? So it seems natural for me to track all possibilities of the last 3 outcomes. But is that the minimal way to do so? Do I have to track everything? I mean, do I have to track all possibilities of the last 3 coin tosses? The answer is no. Because, right, if you think about it for a while, you see that what is really relevant is this one, right? So, sorry, it's rather, right? So you have a head, right, to begin with. So let me try to think. So you have sorry, like this one. So star here represents whatever, right? Head or tail is fine. This, right? What does this represent? This represents you have the first head in your run, right? And then what's the next one? The next one is head, tail, then head. Okay. And finally, right, what's the state that tells you that you have nothing going on? You only need these 4 to track head. So, right, actually also, this goes back to maybe Kathy's question that if you're very sure that all you want to track is head, then this is all you need. But of course, if you want to track head or head, tail, head, then you have to design it differently. But if you want to track head, that's all you need. Do you understand? And right, again, to make sure that, right, this is enough, let's see if we can write down a transition matrix. So, right, let's call state 0 as star tail. State 1, right, is tail head star. State 2 as head tail. State 3 as head. And notice now, right, my notation is also very suggestive. 0 means I have nothing in my pattern. 1 as I have a head in my pattern. 2 heads. 3, I'm completed, right? Can I write down the transition matrix? What would the first row be? Q, P, 0, 0, right? Where Q is 1 minus P. Q, 0, P, 0. 0, Q, right? Hold on. So if I'm here, sorry, let me just check. If I'm here, right, I can either get tail, head, tail, which is that one, or I can get tail, head, head. That's correct. With tail, head, head, I can go there. Sorry, this is P. Or if I get head, head, tail, I go back to state 0. Sorry. And then this is head, head. So, well, you know, I could try the transition if I want, but it's P, 0, 0, Q. Right? You understand?
That looks good, but quick question. With
Yeah.
your logic, do you think we could reduce the problem of finding the first time to any of the patterns, like what is it, THT, for example, into just 4 states?
Yeah.
Yeah,
If
right?
it's a single pattern, yes. If you mix the patterns, then we have to think about it. I'm not so sure.
Okay.
But it's a single pattern, then this is it. Okay. For example, right? Let's kind of go with what you said. If it's THT that we're looking for, then what do you think? How do you think we should encode the state?
Star star H star
Wait, hold on. Star H.
yeah, so that's the failure case. And then
Okay.
star star T, you're slowly building the pattern, right? And then star TH, you're making even more progress in the pattern. And then you found the pattern, so THT.
Yeah, I think this seems right. Do we agree that this would be the base to track this? Right? Yeah, so exactly. If you follow this logic, right, you can do. But notice, right, an interesting thing is even though we read the pattern right to left because it's the last one, you build a pattern up sort of like left to right. Right? Just to point that out. Okay. And now, right, let's kind of see another benefit of doing this thing. So remember, so if I let me say that this is my X, right? And this also corresponds to a coin toss, right? Where do I start the chain? Do I have to start a chain at time 3? Or can I start a chain earlier than that? Let's say, right? What if I want probability, let's say x3 equals to 2? Here's the thing, right? So this chain, even though it also kind of do the track the pattern, you can kind of imagine that at the beginning, right? Like at initial state, you can assume, or this actually correspond to initially you're at no pattern. You can do that. And so if you multiply it 1 time, it will land you on one of these patterns. And then if you multiply it 2 times, 3 times, so this is p cubed 0, 2. Do we understand? So the beauty of right tracking this pattern is you don't need to have that. You can check what I say here. It's a bit, you have to think about. But the fact that the 0 here is not just this, is also kind of measure no pattern. And this tells you that it's really about one head in the pattern in the right place. That's really it, etc. And so, right, to conclude the question, and we'll go back to this next time, you will turn this into a matrix Q by QP00, Q0P0, Q00P0001, right? Because we are tracking 3 heads or whatever you want, right? And then the answer you want, let's say probability, let's say n head equals to 8. It'll be Q to the 8 0 3 minus Q to the 7 0 3, like that. So the point is, if with efficient modeling, right, or with the correct modeling, the answer becomes much more elegant, much simpler, right? Even surprising thing like initial distribution, you can do away with, because basically your state means much more than just three coin toss. It means that you have nothing in your pattern, 1 head in your pattern, 2 heads in your pattern, that kind of thing. So, all right. Any question? All right. So, if not, right, let's stop here. And well, we have 3 minutes. So let me see. I think I just want to run through a slide real quick and just show you that that was that. Right. So we were saying the growth, right? The initial distribution. Right. So that will go with pattern length linearly, right? And so what I was just telling you. And so, yeah, I think, right, I even kind of say that, right? I didn't bother, but yeah, so the understanding is that, right? And then that. Okay. We're good. So yeah, if you have any question, do ask. If not, we'll continue on Monday. All right.
Thank you.
Sure.
Thank you, Professor.
Thank you,
Yep.
Professor.
Yeah.
Thank you.
Yeah.